Hi everyone, it's Matt Cicchini here, and I'm excited to talk to you today about unlocking the data behind the glass and how we can empower this agentic future of pathology. So let's hop right into it. So I have some disclosures, but they're not relevant to the content of this presentation. And I'm going to show a number of tools and systems here, but I'm not endorsing or recommending any of these specific things. And I think one of the most important disclosures here is I think AI is super cool. And before we start, I just want to lay the groundwork of that. I really believe in an AI augmented future and not an AI replacement future. And I think this is an important point because some of the tools and the systems I'm going to show are extremely capable. And this is a really can be scary to some people in that, you can just internalize, well, what does this mean for my job or my career? And I think we really need to rethink this in that not how can we compete with AI, but how can we be augmented by AI? And I'll try and weave that through the presentation. So we're going to go on a bit of a journey here. Just note all the images here are actually generated by AI here that I think kind of lend a nice kind of creative landscape to the presentation here. We might not get through all of it, but that's okay. So we're going to talk about the current state of AI, digital pathology. We're going to talk about how does the current generation of tools work, and how can you use these advanced tools in pathology, and what does the future of AI look like? And we'll give a vision for 2030. So I like to start my talks with kind of one of the coolest or most interesting thing I'm doing with AI these days. And the one thing is I actually don't write code, but now you don't no longer need to. There's this rise of these programs that are called vibe coding programs, where you can actually generate really functional programs that work, or at least prototypes, with a simple amount of text. And so this is an example where I was trying to build an app that helps people train in reporting PDL1 scoring. It's something I've been trying to do for some time. And I've really been blocked on it because I really needed a software developer to develop it for me. But I use this tool here called Replit, and you can see here on the left, I just described what I wanted this to be, and then it actually just goes along and it actually makes this here for me. And then I end up with a functional app here that I can then score and practice PDL1. And so that I can then deploy this, and then I'm now using this, and some of my peers are learning how to score PDL1 with this tool. So I think this just really showcases what you can do. Some other things that you can do with these tools is these AI tools can now actually use computers. So I think this is actually a really interesting use case here, where so this they're asking you to find the best time to see the San Francisco sunrise at Golden Gate Bridge. So basically, does a search, and then it actually finds it out, and then actually makes the calendar one person. So you can really see how some of these really use cases could be truly transformative in our workflows. But I did want to contrast that with the fact that these things are not perfect. And so this is an example here from the same company, Anthropic, showing a additional computer use case. And so this, in this case, it was actually trying to make a website here. And you can see here it's working on the website, but then it actually just gets completely sidetracked and just goes to Google and just starts randomly looking up pictures of Yellowstone National Park. I don't know why. Maybe it really wants to take a trip there, but it kind of completely went off the rails. And this is a really important part with these AI agents is that when they work, they can work great, but they can actually fail quite spectacularly as well. So it's something that is really important to keep an eye on when you're using these. So what about the pathology lab? So, I'm a pathologist. I work every day. I have an analog microscope in my office. I look at my slides, and we're in the process of undergoing digitization. And so then I will look at slides on a computer screen. So have we accomplished our mission here? I made a kind of a joking image here that, I don't really think so. I think just replacing my analog microscope with me looking at the slides on a digital screen, I don't really think is the transformational gains that we really envision with some of these digital pathology tools. And I really think that digital scanning is really the first step on a long journey of digital transformation. And that's really how I like to frame it, is that, yes, we need to unlock the data behind the glass to allow us to use these tools, but really the gains that you're going to see are really the things you're going to do after the fact. And that's what I want to talk about today. And there's this really amazing amount of data that we can unlock behind these slides. And what I want to show you is just kind of some brief glimpses into some of the things that we can do with this data once we digitize it and once we get it out of this analog microscope, because an analog microscope is essentially zero compatibility with any AI tools, that all the data is actually locked behind that cover slip and that we really can't assess it for any of these tools. And so just to give you a sense of the amount of data, I'm sure many people in the audience already realize that, if we're comparing radiology and pathology size of CT scan, it can be on order of 35 megabytes. Depending on how you scan the slide, you're looking at a few gigabytes to scan the slides. And so I just put this in for audiences, especially in Canada where I work, just to kind of compare the relative things. So if you compare, so in my hospital, we're projecting to scan about 1.25 petabytes of data a year. So that's actually 10 times the size of the entire Netflix library. And then in my institution we have a provincial radiology storage, and so we will be producing more data than all the province in radiology. And we project that within 20 years of storage, that we may have more data than Google Maps. So that is, depending on the audience, that can be really scary. And the administrators, I show a very different side to them, but this can be a very scary thing for them. But to me, this is actually quite exciting. And it really it's not the amount of data here; it's just the amount of data that we can use for all these tools and downstream applications. Um, and so, how can we use these? And so, I actually conceptualize pathology kind of as this factory, right? Where we take specimens and the inputs, we then do a bunch of processing steps, and then our output is reports, right? And we're increasingly stretched by getting more and more specimens, asked to do more and more processes, and being asked to produce more and more reports. So how do we make this process more efficiently? Traditionally in pathology, we've really thought about this as this linear flow where a specimen comes in, it's gross, we generate these slides, we scan them, pathologist might order things, we have to go generate more slides. It all just dictates a report and it turns into a report, really. And this really like serial flow doesn't really allow for any parallelization or rapid movement through this. And so I think we can start to change this, and not just that we have this simple linear flow, but we can actually augment this by these agentic tools that can really help us move some of these things along. And I'll showcase some of these tools that I think that we can really utilize to help push this along. And a lot of these tools don't exist yet, but I think there's a really opportunity to build these tools that really transform how we do pathology to really direct cases through this pipeline in a much more efficient way. So what is an agent? So this is a definition from Anthropic, which is one of the leading AI companies. And so their definition is that agents are systems where large language models, which are things like ChatGPT, dynamically direct their own processes and tool usage, maintaining control over how they accomplish tasks. So you can think about this as we take data in, there's an LLM there, and then it produces an output, just kind of like our output of our factory, right? We take specimens in and we get reports out. And so an agent has a similar thing, but it can do a number of things. So the one thing is it can retrieve information. It can use tools. These tools could be different things like what time is it? Or it could be an internet search on a specific topic. And it has the ability of memory. So as it runs through these tasks over and over again, it has the ability to capture memories and improve on this. And so this is kind of the basis of an agent. And these agentic tools are actually getting exponentially better here. And so this graph here on the y-axis is the length of tasks that AIs can do. So this is how long it would take a human to complete that task that they can reliably do most of the time. And if you look back to the early days with the early versions of ChatGPT, GPT-2 and 3, really they couldn't do any task that at all. Really, these things could just complete sentences, partially. And then we start to see some little bit of function around the GPT-4 era. And then we're kind of following this exponential curve. But in the most recent models, with these reasoning models of O1, O4, and O3, which are ChatGPT's reasoning models, and the Claude 3.7 model from Anthropic, we're really jumping off the curve. And that the best performant models can do things that would take a human, 1 to 2 hours already. And you can see the pace at which these curves are really going up. And so this kind of scaling of these agentic capacity is something that I'm really excited about. And so some basic terminology here that we're going to talk about. And so what is artificial intelligence? Artificial intelligence is so you kind of think of it as a good Venn diagram where artificial intelligence is kind of this big picture. Machine learning is a subset of that. Neural networks is a subset of that. And deep learning is a subset of that. And then you can kind of think of them as these neural networks where you have these input layers, these hidden layers in the middle, and then this kind of output at the end. And so it kind of works like your brain, except that we have lots and lots of these layers all in the system. And so what are these large language models? And so these large language models are something called generative pre-trained transformers. So generative means it makes stuff up or guesses what you want to hear. And then pre-trained means it was trained on a massive amount of data. In fact, most of these models have actually run out of data and they've been essentially trained on anything that humans have ever written. And transformers are the underlying architecture that for these systems. And what they do is they work by taking an input of text and predicting the next token or word. And they utilize this transform architecture that we'll talk about in a couple upcoming slides. And one way to kind of think about their capacity is the relative processing power of them. So you can think about the number of parameters within the model, and then this varies where, the more early models, had had about the processing power of a honeybee, whereas the more recent models have about the processing power of a squirrel brain. And so this is just a diagram of the transform architecture of it. I won't go into too much detail, but as a cool way of understanding it, I actually had one of the large language models actually describe it to me as if I was a pathologist, which is kind of a nice hack that you could take a really complex thing and have it described to you in a different way. But it basically says, look at the left side here. This is the encoding. So imagine you have a specimen, you're breaking up into individual slides or blocks. So that you can look at them individually. This is kind of the tokenization part. And on the right side here is a decoder. So then you examine those slides or blocks, and within the context of all the information you know about microscopy and stains and IHC. And then you put that together to predict the diagnosis or the classification of that slide based on all this information to give us a single output. One important part is the tokenization. And so what we do is we take words or language, and then these are each broken up into individual tokens. And these large language models can connect them together with varying strength. And so it connects aliens with extraterrestrials in this kind of weird sentence here. But the cool thing is that it can connect them over a very large range. So you can give it the entire Lord of the Rings trilogy, and it can connect the very first word with the very last word together. And that's where you get a lot of power from these models as well. It's kind of long range attentional mechanisms. They're not perfect though, and this is kind of a classic example of things that large language models typically get wrong. So if you ask it a question of how many R's are in strawberry, the so what it's doing is it's just looking at strawberry as one token. And so it's not realizing it needs to break that word up into all the letters of it and then count. And so classically, these models would actually get this all wrong and they would just hallucinate and give different numbers of R's in strawberry. But this has changed with these reasoning models. And so these reasoning models can now not just spit out an answer, but really think about it. And so this is the response when you give it to a reasoning model is it actually realizes it has to break up this word and spell it out individually. And so it spells out strawberry here, as you can see, and then proceeds to count the number of R's in strawberry. And so these reasoning models have really been a big shift in what we can do with these things. And so this is just kind of a diagram here showing how a non-reasoning versus a reasoning model works. And on the bottom here, so what we're basically doing is a non-reasoning model. Most of the compute is actually spent on the pre-training. So this is when we're looking at all that massive amount of data from the internet, and not very much time is spent on inference or thinking about the problem. Whereas reasoning models, most of the time is actually spent on thinking about the problem in this inference or test time. And what they've actually found is that the longer these models actually think about the answer, the better they actually perform on some of these tests. So that's kind of the baseline of how these things work. And so there's tons of models here. I'm not going to go through the exhaustive slide. Just some highlights here. So the OpenAI is the one we often think about for the Chat GPT. They have multiple series. The O series are their reasoning models. GPT 4.0 is kind of their flagship model. GPT 4.5, they kind of released for a bit, but now they're actually blending that into 4.0. One of the points here is that the naming conventions for these are really confusing and are kind of tough, but I think this is actually going to all become much easier. So OpenAI has already talked about how they're going to condense all their models into one, where it'll actually just use these different models in a way to answer your question the best way possible. The Gemini are Google's models. The Gemini 2.5 Pro is a really good model. I really like it, especially for long tasks. So if you have a large number of PDFs or video and you wanted to analyze it, that can be really good. And then Claude is the kind of number one agent for coding. Grok is the agent that's linked to Twitter or X, and it has the benefit of getting better access to real-time data. Meta has this Llama model, and they've just released a new one, which has a very large context window, so it can take up to 10 million tokens at once. And DeepSeek is the model of China that has been really performant and can be quite good as well. So, but what about pathology? Let's get back into pathology. What can these do in the pathology world? And so this image is actually a few years old now. And so this is when these tools first started being able to analyze images. And I gave it this image here of a histology section of the lung. And I honestly, when I put it in there, I just said, "What is this image?" And I thought it was actually going to just say this is a bunch of purple squiggly lines. But in fact, it actually correctly identified that this was lung tissue and the H&E stain, and told me that was relatively normal. And this was one of those magical moments to me of the really power of these. And so my lab did an initial study where we actually tested real world performance of this versus pathologists, and found that GPT-4 actually performed and exceeded expectations for a senior pathology resident. Um, but and so these things are quite powerful, and there's a lot of things that we can do with these. But there's some guiding principles that we should think about when we're using these. The one and most important thing is that they can hallucinate and provide confidently wrong answers. And when you use these, you're responsible for everything that they do. And you can think of them like this eager intern, and do not upload patient or trainee data or clinical information to these LLMs. This is changing a little bit if you have institutional approval and you have this set up in a way that is actually compliant with guidelines. So just to make sure you check into this before you use this, and ensure that your instance of this is compliant. These things are improving at a rapid pace. What they can't do today, they might be able to do tomorrow. The prompts that you put in this can matter. This is becoming a little bit less important as these models get better. And if you don't get what you want, just keep trying again. Sometimes you just have to ask it to kind of give you some help on helping you get what you want. So what about pathology models? There's a number of foundation models in pathology. I'm going to show a bit of stuff here with Virchow here. And so what can we do with some of these tools? So I've talked a lot about these tools, but let's bring it back into pathology and let's make it practical for what you can do. And so, really, the first step is digital pathology, as we said at the beginning. We need to have these images that we can then use. And I made this graph in the past of that. I think there's really going to be this big divide as we move into this larger digital space. There's going to be things that we can really just do so much better in a digital world that I think are going to really drive that. I'm going to try and show some examples. And so, the first thing I just wanted to show is how easy it is to set some of these things up. So this is work I did with one of our pathology residents back in Canada. And we really wanted to test out one of these foundation models and apply it to our work. So we utilized the Virchow model, which is available on Hugging Face, which is a place that you can download them. It has an open use that you can actually use for commercial purposes as well if you wish. And it's actually a fairly small model. I was actually able to run it on a PC that I actually bought from Best Buy. So this is not any kind of crazy AI computer. This is literally just a gaming computer that I bought from Best Buy. And we trained it on a small number of cases, only 30 cases. And we wanted to start off with a relatively easy but important task of identifying basal cell carcinoma on frozen section. Because this is something that we're facing with pathologists, and these results can really matter when they're taking off frozen sections around sensitive areas like the head or neck. And so it's just an example of this tool. So we're looking at these margins here for these cases. And then so the left here is a negative margin. And the tricky things in these is you have all these little hair follicles here that can look like BCC. And then a positive here, you can see at low power are these little kind of purple blue areas that are actually the basal cell carcinoma. And so if we look at it a little bit closer, you can better see that the negative one just has these hair follicles, and the right here we have these BCCs. But these can be quite tricky, especially when you only have small areas of it. And also, it can be hard to convey the results to the surgeon as well, just how much tumor is there and where is the tumor actually localized. So we sought to kind of solve both those problems. And so in this case here, we actually we train these cases, and so this is just it running through the cases. So it breaks each of these up into tiles, and then it tries to classify each of these tiles to see if there's any tumor. And so in this negative case, it correctly identifies that there's no tumor here in the slide. Whereas in the positive case, what we see here is that it actually maps out where the tumor is, and you can actually see where that actually maps out correctly here, and it finds even these small little areas of tumor here on the right. And so this can be really helpful to find this, especially when there's only focal tumor there. And the other thing that we're exploring is a way to provide this to the surgeons as well, to better understand where their margin positivity is, and the extent of margin positivity in a real-time and effective way for the surgical team. And so this is something that we built within a few weeks using a computer that we got from Best Buy, using a tool that we downloaded it off an open source. The other thing we've done some other things of getting to that agentic workflow. So one thing we face in pathology is that when you don't have enough levels, you don't have a full face of the margin, and so we built here an algorithm that actually detects the margin. So you can see here this on the black, and then the tumor, and then can localize them together. And so in this example, it can actually find an area where there's actually tumor touching ink here. And so you can start to see how you can start building some of these tools together to really start auto-completing pathology reports, right? So we can identify tumor, its relationship to the margin, we can get its distribution, so you could start measuring depth and extent of tumor. And this could be, you could really start to see how you can start building these tools into some really transformative workflows. Um, so the other thing is it's not, you don't need fancy AI for all of this, and so some of the other stuff that we do is kind of some simpler image analysis tools that we use, and so we focus on kind of real clinical problems we've had around Ki67, HER2, PDL1, and molecular testing. And what's been really helpful for us is we actually have this brand new position that we call a biomarker analyst. A biomarker, and so our biomarker, we now have two of them, and they're MLTs that have additional graduate training and development and implementation of AI tools, and they've really been transformative in our practice. And so they actually review all of our MMR cases. They do image analysis for Ki67, and we're just launching tests for PDL1 and HER2, and they also run our rapid molecular testing program. And so we use a relatively simple image analysis pipeline where we have a way of classifying positive and negative tumor and stromal cells for our Ki67 pipeline here. And this can be really helpful, especially in these breast cases where you need to report this global average. And you can get these heterogeneous expression of Ki67 across the slide here. But with these tools, you can really get this average and then you can use this. And so this is something we've built in-house and it's run by our biomarker analysts. And then they just push the results to the pathologist. And this has been a really effective way of doing this. And so we just built this as like an in-house lab developed test in here in Canada. So one of the biggest complaints I get from my pathology peers is when we're going to make a tool that solves PDL1 reporting. And so the first thing that we did here is we actually thought, well, what's the hard part of it? So on the left here is actually the scoring system for PDL1, whereas the numerator is essentially the number of positive tumor cells plus positive immune cells, and the denominator is the total number of tumor cells times 100. And in this case, the cutoffs for many cases are like less than one or greater than 10. So the numbers are low. And so to get a positive case, you actually need relatively few cells in the numerator. But the challenge is actually determining the denominator of this fraction. And so we just built a simple tool here where it actually calculates the denominator for you. And so on the upper left here, as you move this around, it's actually calculating based on how many tumor cells here on this image, how many cells you need in the numerator to actually pass this positive threshold. So you can see here as we move it around, this is going to update, and then you can see how it would be very easy for the user to actually then just say, oh yeah, obviously there's more than 75 positive tumor cells here, so it's greater than 10. And so we're currently exploring this in a trial to see whether this actually improves the intra-observer variability between pathologists and reporting PDL1 testing. And so let's go back to those AI tools. And so as a pathologist, how can I use these tools as a way to solve some real world problems? And so the current way that I tackle a challenging case is I go to a textbook, or if I'm really stuck, I might go to Google and say, what is this weird tumor? And, if I can't then figure out, I probably put it in the mail and send it to someone else to see if they can help solve it for me. But this is changing a bit with these reasoning models. I found that these reasoning models are really great thought partners that can really help me work through cases. And that's the main use that I have of them, where I'm using them to brainstorm. And so I don't put any patient information in it, but I'll just describe the scenario I have, that I have this high-grade tumor that's expressing this random spectrum of stains, and can you help me brainstorm differentials and things? And these are things that I would have previously put in Google searches and serially done it, but I find that these just work way better. And so this is an example here where I actually gave it one of the most challenging cases, and then actually correctly identified that it was a SMARCA4 deficient tumor, which is an incredibly rare and challenging diagnosis to make. And it correctly will lead me towards those. And you can really see how this could really help these pathologist workflows where it could really augment them. We did some work here in my lab around picking the right stain, and it can actually help you decide on IHC panels in more of an efficient way. And one of the biggest unlocks for me has really been these deep research tools. And so these deep research tools are basically an AI that has access to search as well as reasoning. And then it can really think through a problem. And so I recently had to do a talk on the genetics of interstitial lung disease, and it was an area that I was somewhat unfamiliar with. And so this is just through ChatGPT. And the way I actually got familiar with this is I just did these serial deep research queries, kind of getting the initial landscape of it, and then kind of diving down deeper. And you can see it actually cites all the papers where it's getting from, and then you can go and pull those papers. And so I was very effectively able to get up to date on literature and really kind of prepare this talk in a really efficient way. And these tools are actually really, really good. And so this is just their performance on this exam that's called Humanities Last Exam. And this deep research is actually, you can see how much better it's performing some of these other things. And these are like really hard questions. These are some of the examples of the questions that it got. Translating this Roman inscription or figuring out how many tendons this hummingbird has. And so there's really high performance of these tools for even these really challenging things. And so I use that a lot. There's also like quicker versions of it as well to run. And so I have to access these through Perplexity, which is basically an AI search. And so these are just some examples of things I've used in my practice to help me. And so I recently had a lipoma. I don't do a lot of soft tissue, but it was rather large, and I knew that I needed to do MDM2 fish testing when it reached a certain size. And so instead of Googling it, I just put this into Perplexity and it actually came up with the results here. And then you can go back and check these citations, determine the size at which you have to start considering fish testing a lipoma. The other thing is, I was doing a sebaceous carcinoma that actually had loss of MLH1 and PMS2 instead of MSH2 and 6, and I wanted to learn more about that. So I did this query here to kind of give me some more information around that and the frequency of that happening. The other cool thing that I've really leveraged in pathology is how can we use the multimodal capacity of these tools to really help us understand things and augment our jobs. And so one thing I actually really enjoy doing, and I think this is going to be transformative, is this idea of a stream of consciousness dictation. So as we're, typically a lot of our workflows is we're looking down the microscope, we're seeing a bunch of things, it's kind of processing through our brain. And then we kind of need to task switch, and then we need to say, okay, I'm going to turn this into a report. And that task switching can be really inefficient, right? Even if you're using a system like Dragon to put it in, you have to make sure Dragon's putting it in the right spot. You have to make sure that you're actually narrating it in the correct way in which you want it to appear in the report. If you're doing a synoptic, you may actually have to click through it. And so what we've actually been exploring is, can I just give my random stream of consciousness that's not a good dictation as I'm just looking under the microscope, saying things like, oh, it looks like it's an adenocarcinoma. Okay, it looks like it's beyond the outer elastic layer of the visceral pleural in the lung. And then can it actually just make a pathology report just from my random kind of stream of consciousness as I'm looking down the microscope? So we tested this out here. And then what I just want to show you here is it actually created a full synoptic report here just based on my stream of consciousness dictation. In our initial pilot of this, it seems to be performing extremely well, where these tools just have a great way of taking this voice input and actually turning into a really effective thing. And so for me, I think this is going to be really transformative. Instead of having to carefully watch the Dragon dictation to make sure that's putting the right things in, I can just kind of say what I'm seeing in a much more natural way, and then I can give it some parameters and it will actually turn into a really structured report. So the multimodal assistant piece, I think, is really exciting and really cool. And so I'm using here the Gemini Stream real time, and so it can actually see my screen and actually talk to me at the same time. And so just for this demo, I did not use any PHI. So this is actually a teaching slide and a synthetic report that I just made up with random data, just to showcase the potential of some of these tools. And so what it's doing is it's watching my screen here, and then it's
Okay,
going
so I'm going
to
to
start
test out
talking
here
to me.
the Google real-time stream thing here. So I'm using Google AI Studio, and so I'm going to go from here.
So it should now
Okay,
talk to me.
let's begin with the
This is
specimen
the
section
AI
of the
talking.
report. Can you tell me the procedure that was performed?
1 second here. I'm going to show you the gross description of the case here. Can you
So
see
now
that
it's going to
there?
be looking at the gross description here, and then it can
Okay,
see
I see
this.
the pathology report. Based on the information, the procedure is
And so it's actively
anything in the
reading
gross description.
and seeing what I'm looking at the same time. And then as we move along, I'm actually going to show it the histology here, and it's actually able to do a fair bit of interpreting this as well. So in this aspect, I'm asking it to figure out what kind of cancer this is here.
So this is one view here of an area, and then let's see, we have some areas that look like this here. I don't know, what do you think the histologic type is?
Okay, thank you for sharing the slide view. Based on the images and the papillary growth pattern, it appears to be an adenocarcinoma. Does that align with your assessment?
Yeah, so it correctly identifies just by looking at the slide here with me real time as I was moving around this adenocarcinoma, and does actually pick up that there's some papillary areas to this as well. A lot of it is more acinar, and we continue along the discussion, but you can really see how these tools, even in their current state, could really be helpful in a lot of our workflows. We're also exploring this in teaching medical students. So I have two medical students working with me trying to test the fidelity of these tools of actually giving them accurate information. Because one of the problems is when you're first approaching pathology, especially today where most of the histology curriculum has been removed, that it can be really overwhelming for students. And so we're looking at whether these tools can actually provide them with insightful information and understanding to really help and augment their learning of this. And just like end here with some fun stuff is that it actually will remix images for you as well. So this is an image of usual interstitial pneumonia, and it can actually turn these areas into looking like letters of UIP. The people say that these are honeycomb chains, and this should be the size a bee could fit in. You can even make a bee fitting into it. So I think some of these tools can really transform what we can do here in pathology. So I have a few more slides here. I don't want to spend too much time on them, but just kind of show some of the other things that you can do with these and kind of give you an idea of what is possible with this once we digitize the data. So one thing that we often do in pathology is we have to find these rare elements, like we're trying to find Waldo on this thing. But in starting to find Waldo, we're looking for these little fragments of tumor within lymph nodes. And there's AI tools that do this quite well. So this goes all the way back to 2017, and many of these have been commercialized as well. But we were actually really interested in my lab is how do pathologists do this and how can we integrate humans with that? And so one of my really talented PhD students has actually been utilizing these eye tracking systems and to actually better understand how we do various pathologist tasks. And we actually first started off with seeing how pathologists look for where's Waldo. It is a fun way to kind of actually to just test out the system. And it turns out pathologists actually look for Waldo differently than non-pathologists. So this is the eye gaze of a pathologist searching for Waldo. So you see that's really kind of has this kind of raster scan, this really logical approach, and our eyes actually move faster, and we fixate for a shorter amount of time on individual spots. Where if you compare the non-pathologists here, it's quite haphazard, and the size of these circles are larger, so they're spending larger on an individual time, and their eyes actually move smaller. And so, being a professional pathologist actually makes you a better Waldo finder, I guess. And so, I like to joke that I'm a professional Waldo finder, and I guess there is some truth to that. But one of the cool things is when we looked at different tasks that pathologists have to do, like finding mitotic figures, they are actually able to see these beyond their foveated vision. So when the pathologist is looking for Waldo, we don't see that in our peripheral vision. We basically have to have our eyes land on Waldo in order for us to actually recognize it. Whereas mitotic figures, we're actually able to pick up these in our peripheral vision. So this is basically this graph here is actually showing the jump where we jumped from one area to the next when we saw the mitotic figure. And so there was this really substantial area that we could actually pick these up and actually move through. And so this is a really interesting thing. And there's this, and we're doing more and more around this eye tracking piece to really understand this. This is kind of like the window into the mind of the pathologist. As part of this as well, we really had a question around like what was the right screen size for this, and so we decided to do a small study of this to look at, if you give pathologists different screen sizes, like where do they look? And we found this interesting feature, whereas if you give them really really tiny screens, they'll look at all the information screen, but as you start to get larger, so at 24 or 36 inches here, 24 32 inches here, there starts to be this gap around the outside where the vision actually doesn't actually see. And so, they actually still performed well on the task of finding tumor and lymph nodes in this case. But to me, it was actually a little bit of a point that, potentially the bigger giant screens are not always better in that, especially if you're using that primarily for your viewer for digital pathology, that you may not want to max it out because your eyes are really not going to foveate on the outside of the screen here, especially in these really large monitor sizes. And just ending with one last thing, which is kind of a fun thing, and the kind of one of the more crazy things my lab has done.
This
And so I always like to play with data, and I think this is a nice use case of what you can do with digital pathology slides. And so in my lab, we actually turned pathology into songs. So we broke up the slides here into individual tiles, and then you can do a feature extraction from these tiles, and then you can assign these features to different instruments. And so we assign this to a piano, a violin, and a harp. And so this then actually creates a song out of the slide. And so what you're going to hear here is we're going to move from tumor into non-tumor. And I want you to kind of listen for the difference. So here you go. So did you hear the transition here? So this is tumor, a bit darker. And then lighter is the background lung parenchyma. And so I think this is a nice example of once the data is digital, you can do anything with it. You can even turn it into a song. And so I don't think I'll be listening to my slides anytime soon, but I think it shows the power of it. And we actually did a final fun study with this. One of our residents had a bunch of friends that were in the music program at my university. And we actually gave them these songs and we asked, and they had no histology training. And we asked them to listen to these songs and trying to pick up the transition between tumor and non-tumor. And in almost all cases, they were able to get bang on exact the transition. So they could actually hear the difference between tumor and non-tumor, despite not having any formal pathology training. So let's just end with kind of a vision of what could pathology look like in the future. Maybe working with an AI tool that can prioritize all your cases because it can figure out and see what's on the slide and gives you this really prioritized list. It can then do these deep research queries and really help you be the thought partner and help you work through a case. And then it can then search the archive and then it can find similar cases. It can help you with a task, like maybe you need to write an REB for a research study, and it can help you with that. And so I think this is some of the tip of the iceberg, and I'd love to chat more about this. But I think the future is really quite exciting. I think, and I just wanted to put some of these ideas to kind of get your brain spinning of what can you do. And a lot of these tools you can use right now. You don't need any giant implementation or anything. These are things that you can do now. And I think that these things are all prerequisites of scanning the slide. And so when I'm pitching digital pathology to my institution, this is really one of the key foundational aspects I had is that we need to do digital pathology so that we can keep up with where our field is going and the way things are moving. So thanks so much for your time, and I hope you enjoyed this talk, and all the best.